In this episode, we unlock a mysterious mathematical code found in nature, numbers, and quantum physics. From the chaotic beauty of prime vortex maps to the stable swirling electron flows in quantum materials, we explore the deep recursive principles that may reveal a hidden law of the universe. Are prime numbers secretly swirling in chaos like a tornado? Why do electrons in exotic materials form quantum vortices? Join us on this mind-expanding journey as we uncover hidden swirls that attempts to find nature's deepest secrets.
All right, so get this. We're going deep into prime numbers today, but not just any prime number. This one's a little rebellious, you know. It's the story of 9973 and how it's kind of shaking up what we think about randomness.
It really is quite fascinating. You see, we often think that making really random numbers needs like these super complex algorithms, especially for things like AI or simulations. But 9973 kind of throws a wrench into that whole idea.
So are you saying no more long, complicated equations, just this one prime number doing all the work?
Well, there's still an equation, but it's surprisingly simple. Like, you take any number, multiply it by 9973, and then you just keep the decimal part of the answer. Do that over and over, and you get a sequence of numbers that, well, at first glance, seem totally random.
Okay, I gotta admit, I'm a little skeptical here. How do we know these numbers are actually random, like truly random?
That's what's so amazing. 9973 has been put through a whole bunch of statistical tests, and it passes them with flying colors. The same tests used to check those hardcore cryptographic ciphers, the ones that keep our online stuff safe.
Whoa, whoa, whoa. So this prime number, the seemingly simple one, it's going head-to-head with the heavy hitters of randomness. I'm starting to see why this is a deep dive.
Exactly. And it gets even wilder. When you compare 9973 to a well-known cipher, something like Cha-Cha 20, well, in some tests, 9973 actually did better, showing even more randomness.
Hold on, are we saying this prime number in this simple equation could actually beat complex algorithms built for security?
It's a question that has everyone talking. It's like finding out that a simple hand-crank generator can, under certain circumstances, make more electricity than a huge power plant. It really makes you rethink where complexity comes from and what randomness really is.
Okay, you officially blew my mind, but how is this even possible? What makes 9973 so special?
Well, there's some theories. One is that it's very close to a power of 2. 9973 is just a little bit bigger than 8192, which is 2 to the 13th power. And prime numbers near powers of 2, they often have, well, interesting properties, especially when it comes to making random numbers.
So being in the right neighborhood on the number line gives 9973 this edge.
You got it. It's like being close to that power of 2. Gives it a special mathematical advantage for making chaotic, unpredictable sequences.
Okay. That's one piece of the puzzle. What else is making 9973 so good at this randomness thing?
Another clue is in its binary form. When you write 9973 using only ones and zeros, you find a really balanced spread of those digits.
So it's not just about the number itself, but also about its deeper structure, right?
Exactly. Think of it like shuffling cards. A well-shuffled deck should have the suits and numbers spread out evenly, right? That balance, that's what makes picking a card random. And it's similar with 9973. That balanced binary form might be why it can create these unpredictable number sequences.
Okay, I'm seeing how the pieces fit together. This prime number, it's right next to a power of 2. It's got this balanced structure at its core. It's like 9973 is a recipe for randomness.
That's a great way to put it. But there's one more ingredient we need to talk about, something called multiplicative order. Now, this one gets a bit technical, but it's really important for understanding 9973's, well, it's magic.
All right, I'm ready to dive deeper. Hit me with it.
All right, so think of it this way. Imagine drawing a circle and marking points around it. Each time you multiply a number by your prime, you move to a new point on the circle. Now, the multiplicative order tells you how many points you'll hit before you start repeating the pattern.
So a bigger multiplicative order means you get more unique numbers before the sequence starts looping, right?
That's right. In 9973, it has a really high multiplicative order, so it makes a huge number of unique numbers before any repetition. This makes the sequences it creates even more random and unpredictable.
So 9973 takes us on this crazy tour of the number line, hitting all these different points before it finally comes back around. It's a long and unpredictable journey, which is exactly what we want for true randomness.
Exactly. That's what makes 9973 so remarkable. It seems like such a simple prime number, but it makes us rethink what we know about randomness and complexity.
9973 could maybe simplify that whole process.
Exactly. Because that equation using 9973 is so simple, it's not a big burden on computers. It could make those simulations run way faster, maybe even open up new possibilities for more detailed modeling.
Now, earlier we were talking about how 99973 aced those tests, those same ones used for cryptographic ciphers. So does that mean we could use it for, like, actual encryption? Is this the future of cybersecurity or something?
Well, that's where things get a bit more complicated. 9973 did great on those first tests, but remember, it did show a couple weaknesses when we dug deeper.
Oh, right. The runs test and that autocorrelation test. Can you remind me what those were all about?
Sure, so think of the runs test as looking for patterns in the sequence, where the numbers keep going up or keep going down for, like, a suspiciously long time. It's like if you flip a coin and get heads 10 times in a row, you start to wonder if the coin is actually fair, right?
And 9973 didn't quite ace that one.
It did okay, but there were a few spots where it seemed to have a little bias towards these runs, those ordered bits. And that's a bit of a red flag for encryption because a really smart attacker could maybe use those patterns to guess the next numbers in the sequence.
Okay, and what about that autocorrelation test? What did that tell us?
That one looks for correlations within the sequence itself. Like imagine you've got this list of random numbers and you shift that list over a bit. The autocorrelation test checks how similar the original list is to the shifted one.
So if they're really similar, it means there's some hidden structure in the randomness, some way to predict it.
Exactly. And 9973 did show some mild correlation when we shifted it in certain ways. Again, it's not a deal breaker for everything, but it could be a weak spot in a high security situation.
So, like, using 9973 for, say, protecting bank transactions or those super secret government messages, probably not the best idea, right?
Let's just say it's not ready for those big leagues yet. But that doesn't mean it's useless for cryptography altogether. It could be really good in some specific areas.
Like what? Where could 9973 still be helpful in the world of encryption?
Think about those situations where you don't have a lot of computing power, like maybe a small gadget, or maybe when speed is super important.
Oh, so like those lightweight cryptography things where you need some protection, but you can't handle the big, complex algorithms.
Right. And that's the main point here. 9973 isn't a solution for everything, but it has the potential to really change some things.
Yeah, like simulations could get faster and more efficient. But you said there was one more really crazy thing about it. What is it about this prime number that's got you like so hooked?
It's how it connects to these really big ideas in physics and math, like quantum mechanics and chaos theory.
All right, now we're really going deep here. But I'm with you if you are. How does a prime number, how does 9973 connect to all that?
Let's start with quantum mechanics. You know, it's all about how at the tiniest level, things get really unpredictable. Like, we can't know everything about a particle, where it is and how it's moving at the same time. There's always some uncertainty, like, baked into reality itself.
And you're saying there's a link between that and our prime number equation.
Yeah, exactly. Think about it. The equation by itself is totally predictable. Same starting number, same sequence every time. But the sequence, the numbers it makes, they seem random, even chaotic, right?
So it's like the equation is a set of rules, like the laws of physics, but somehow those rules lead to these results that we can't predict.
That's it. And that's where chaos theory comes in. It's all about those systems that are super sensitive to, like, the starting point.
Yeah.
Even a tiny change at the beginning can make a huge difference later on.
Oh, like that butterfly effect, right? A butterfly flaps its wings somewhere and then boom, a hurricane pops up on the other side of the world.
Exactly. And it's kind of like that with 9973. It's a simple equation, it's predictable on its own, but the numbers it spits out, they seem to, like, cascade in these unpredictable ways, just like a chaotic system.
So wait, are you saying this prime number is showing us a little piece of that underlying chaos that drives, like, everything, like the weather, the stock market, maybe even like how galaxies form?
It's a really cool idea, isn't it? We tend to think of randomness as like the opposite of order, but maybe it's actually the result of these super complex patterns that we just don't understand yet.
Whoa. I'm getting chills just thinking about it. It's both kind of scary and amazing at the same time.
It is.
That's what I love about these deep dives.
I totally agree. The search for knowledge, it's a journey, not a destination.
All right, now we're really going deep. Like that underlying chaos, like Ever notice those like swirling patterns in nature? It's mesmerizing, right? Like a hurricane when you see it from way up high, or the spiral arms of a galaxy, or even just like a smoke ring hanging in the air.
Right.
Or those complex currents in a really like fast-moving river.
Totally.
There's this cool blend of order and chaos in those kinds of swirls.
Yeah, it's like they're predictable and unpredictable at the same time. It's wild.
Yeah. And the crazy thing is that this tendency towards these like swirl patterns, it's not just something we see out there in the physical world. When you start looking at numbers, like abstract math, and even the really strange world of quantum physics, you find these same kinds of underlying structures popping up.
It's true. It makes you wonder if there's like a more fundamental principle at work here.
Yeah, there's this hidden connection.
Exactly.
So that actually brings us to what we're diving into today.
Okay.
This super unexpected link between two areas that you would think have absolutely nothing to do with each other.
Right.
So we're going to explore the connection between number theory, particularly how prime numbers behave, and topological quantum materials. And it turns out that both of those things are revealing these totally new kinds of swirling structures.
It's fascinating.
Yeah. We want to understand why we see these swirl-like structures popping up in number theory, in the quantum world, and even in stuff we see every day, like fluid flow.
Really?
Yeah. So before we get into all that, there's a big question to think about here.
Okay.
Are these swirling phenomena, like the patterns we see with prime numbers, the way electrons move in those quantum materials, and even just eddies in a stream, are all those just analogies, or do they actually point to a deeper law of nature? Is the universe, like, at its most basic level, built on some kind of swirling recursion?
Wow.
And if it is, can we even find like a single mathematical framework that could explain it all?
That's a big question.
Yeah, and that's some of what we're going to try to tackle today.
Okay, let's start with something we can all picture in our heads.
Okay.
Vortices in fluid dynamics.
Okay.
Like tornadoes, whirlpools, see these all the time.
Yeah.
What's the basic way to understand those?
Yeah, so how do those work, really?
So basically, a vortex in fluid dynamics is a region where the fluid flow is rotating around a central axis.
Okay.
You get these like closed loops of flow, streamlines, that can be amazingly stable.
Okay.
And what's so cool is how they can self-organize. They can become the basic building blocks for way more complex systems.
Okay.
Like the crazy patterns we see in turbulence.
So what actually governs that? What are the rules behind that?
The main principles are the Navier-Stokes equations, which are really hard to solve.
Yeah.
But a lot of times a vortex forms because of instabilities in what we call local shear flows.
Okay, so what is that?
So imagine you've got two layers of fluid and they're sliding past each other at different speeds.
Okay.
And that friction can actually create a spin, a localized swirl.
So like a small amount of friction can make something as powerful as a hurricane.
Exactly, yeah. It's amazing how these small local things can have such a big impact.
Yeah, that is really amazing. Now, this is where it gets really interesting.
Okay.
Because we're going to jump to something that feels totally different, this abstract world of number theory. So you mentioned prime chaos before.
Yeah.
What exactly is that?
So this is where math shows us this behavior.
Okay.
That's surprisingly similar to the chaos we see in real physical systems.
Okay.
Think about a pretty simple math operation called the dyadic map.
Okay.
You take a number that's between 0 and 1, multiply it by 2, and then you just take the fractional part, like the part after the decimal. Yeah. That's what modulo 1 means.
Okay.
And if you keep doing this over and over again, you get this sequence of numbers that looks totally random. But here's the crazy part. If you replace that 2 with any prime number, like 3, 5, 7, you can make sequences that statistically look just like the randomness we see in quantum mechanics.
So like a prime number generating quantum randomness?
Yeah. It's counterintuitive, but it's true.
So where does the swirling come in with all of this?
The swirling here, it's not like a physical rotation.
Okay.
But it's more like you're folding this unit interval over and over again.
Okay. And it's driven by that prime number multiplication?
Yeah, that and the modulo operation.
That's pretty wild.
Oh, yeah. And the last digits of the prime number you use have a huge influence.
So like those digits are controlling the chaos.
Yeah, it's like they act as a vortex core. Influencing the whole structure of that chaotic sequence.
So it's like those tiny little details in the prime number can control how much chaos there is. Like that little initial spin, that can control how powerful a tornado gets.
Yeah, is a good analogy.
Yeah, that's pretty neat. Okay, so we've gone from swirling fluids to these abstract swirls in math that are tied to prime numbers.
Right.
Now let's go to something incredibly tiny.
Okay.
Those quantum tornadoes in momentum space you were talking about.
Yeah. So this is some cutting-edge research
Okay.
in topological quantum materials.
All right.
Specifically in these materials called Weyl and Dirac semimetals,
Okay.
like tantalum arsenide.
Okay.
And researchers have found that the electrons in these materials can actually form swirling patterns. Not in normal space like we're used to, but in what we call momentum space.
Okay, and momentum space is, what is that?
It's like a map that shows all the different speeds
Okay.
an electron can have inside that material.
Okay.
And what they're seeing is a swirl of electron waves inside that momentum domain. And it's driven by something called orbital angular momentum and stabilized by the unique band topology of these materials.
Okay, so instead of swirling air or abstract numbers swirling around,
Yeah.
you've got these electron waves swirling around in momentum space.
Exactly.
So what makes these tornadoes in the quantum world so important?
There's a few things that make them super special.
Okay.
First, they're stabilized by the topology of the material's electronic bands. This topological protection means they're naturally resistant to little disturbances and imperfections,
Okay.
unlike regular electron flow.
Right, so they're really stable.
Yeah.
Okay.
Second, this swirling motion is driven by orbital angular momentum, which is totally separate from the electron spin, which is what spintronics is all about. And this opens up the possibility of a whole new field called orbitronics, where we could use the swirling of electrons
Okay.
for super robust and energy-efficient ways to transfer and store data.
So we've got swirling in fluids,
Right.
this abstract swirling in number theory with the prime numbers.
Yeah.
And now we've got these quantum tornadoes in momentum space. It really seems like there's a similar pattern here in all these different places.
It doesn't it?
Yeah. Is there some kind of universal principle going on here?
I think that's exactly what we're trying to figure out. You start with some kind of constraint or initial condition, like a little bit of shear in a fluid, a certain arrangement of digits in a prime number,
Okay.
or a starting orbital angular momentum in a quantum material. And then you've got this recursive evolution. So the fluid flows according to its own dynamics. The chaotic map keeps repeating, or the quantum system evolves according to the rules of quantum mechanics.
Okay.
And from just repeating those local rules over and over again, you get this stable, large-scale swirl structure.
So it's almost like a tiny swirl seed that grows into this huge organized pattern.
It's a great way to think about it, yeah.
Yeah, and that happens across all these different areas.
Exactly.
You also mentioned something about swirling being like a spectral signature.
Oh, yeah.
So what does that tell us?
So this is a bit more abstract,
Yeah, okay.
but it's really insightful. It suggests that there's this deep connection between the overall swirling structure we see and the fundamental math operators that control how the system behaves.
Okay.
So think of it this way. The specific features of the swirls, like how stable they are, their shape, their energy, all those things are connected to the energy levels, or what we call eigenstates, of these operators. So for example, the way that prime numbers are distributed is deeply connected to the zeros of the Riemann zeta function, which has these spectral-like properties.
Okay.
And similarly, those swirling patterns in quantum tornadoes, those are actually the wave functions of the electrons, or the eigenstates of the material's Hamiltonian, that describes the material's total energy.
Okay, so the swirl it's like a fingerprint.
Yeah, kind of.
It's showing us something about the underlying math of the system.
Exactly.
And you also said that these swirling states are really good at storing information.
That's right.
So why is that?
Because once a vortex forms, it tends to be really stable.
Okay.
Whether it's a long-lasting eddy in a fluid,
Yeah.
the inherent randomness encoded in a prime-based chaotic sequence, or that topologically protected swirl of electrons in momentum space, all of those swirling states can hold on to their structure and can hold on to the information they might be encoding for quite a while. So the swirl itself becomes this robust carrier of a signal.
Okay.
So think of those final digits of the prime number.
Okay.
Like they're adding this specific localized twist every time the map repeats.
Okay.
When you multiply the current number by the the prime, those last digits interact with the fractional part in a really important way.
Okay.
So if those digits have a certain pattern, they can actually make that stretching and folding process stronger,
Okay.
which leads to that strong chaotic behavior.
Yeah.
But if you change those digits or you mask them somehow, you're messing with that little twist. And that can actually disrupt that delicate balance you need for the chaos to keep going. Like stopping that little swirl in the fluid.
Okay.
The tornado never really forms.
Right.
And the flow becomes way more predictable.
Okay, that makes sense. And those quantum tornadoes, you said they were discovered in tantalum arsenide, which is a Weyl semimetal. So what's so special about those types of materials?
They have this unique electronic structure.
Okay.
Where the conduction and valence bands, which are normally separated by an energy gap in insulators and semiconductors, they actually intersect at certain points in momentum space.
Okay, so it's because of the way those bands intersect.
Yeah, and it's that weird behavior at those nodes that allows those swirling patterns to appear.
So you talked about orbital angular momentum, or OAM, being important for making those vortices. And you contrasted that with spintronics, which is based on electron spin. So can you break that down a little more? Like, what's the difference there?
Sure. So electrons have two basic types of angular momentum. Spin, which acts like a tiny little magnet.
Okay.
And orbital angular momentum, which is related to the way the electron's wave function is spread out in space.
Okay.
It's essentially, it's motion around the nucleus, although in this case, we're talking about its motion within the crystal lattice. Spintronics uses the spin of electrons to store and process information, but orbitronics wants to harness the orbital angular momentum.
Okay.
And those quantum tornadoes we're talking about, they happen because electrons have this orbital angular momentum.
Okay.
And because those swirling states are topologically protected, they could be more stable and energy efficient ways to manipulate electrons than just using their charge or their spin.
Okay, that makes sense. So you also made this really cool connection between these chiral, Weyl, and Dirac nodes and magnetic manifolds in momentum space.
Yeah, so basically those Weyl and Dirac nodes act as sources or sinks of what we call Berry curvature in momentum space.
Okay.
You can think of Berry curvature as a magnetic field that acts on the electron waves.
Okay.
This field makes the electron wave functions swirl around those nodes, like how a magnetic field makes charged particles move in circles, and the chirality of the nodes makes sure that those swirls are topologically protected.
Okay.
So that they can't easily be messed up or destroyed without totally changing the band structure of the material.
Okay, so this vision of orbitronics, it's about using this phase swirl, this angular momentum for data storage and transmission.
Exactly.
More efficient electronics.
Yeah.
So we've got these swirling phenomena popping up in these seemingly totally different areas, number theory and quantum physics. We talked about some of the comparisons earlier, but let's revisit that a little bit. What are the main things that connect these phenomena?
So I think the most obvious connection is this idea of recursion and swirl in different spaces.
Okay.
In prime chaos, the recursion is you're just applying that modular arithmetic operation over and over again. And the swirl is how the number evolves within that confined space from 0 to 1.
Okay.
With quantum tornadoes, the recursion is more baked in, I guess you could say, to the way the electron wave functions evolve according to quantum mechanics within that crystal lattice.
Okay.
And the swirl shows up in the momentum space of those electrons.
Okay, so the space where the swirl happens is different. The main idea of this repeating process that leads to a swirling pattern seems to be the same.
Yeah, that's the common thread.
Yeah, okay. And you mentioned the role of spectral geometry, too. As another important overlap.
Yeah, so in both cases, the details of the swirling patterns are really closely tied to the spectral properties of the math operators that control the system.
Okay.
For prime numbers, it's the Riemann zeta function and how its complex zeros are distributed. For quantum tornadoes, it's the material's Hamiltonian and the topological features of its electronic energy bands. So the swirl isn't just some random thing that happens. It's a direct result of the underlying mathematical structure.
Okay. Now let's switch gears and talk about protein folding. So for someone who doesn't spend their days thinking about biochemistry, what's actually happening when a protein folds?
Imagine a protein like a really long chain of beads. Each bead is a different amino acid. And for this chain, this protein, to do its job, it has to fold itself up into this very specific, very intricate three-dimensional shape. And it's not just a random crumpling up either. It's guided by all these little interactions between the amino acids that are close together.
So those amino acids are like little magnets attracting and repelling each other, just trying to figure out how to fit together.
Yeah, that's a great way to think about it. It's
Yeah.
like they're all pushing and pulling on each other, trying to find the most stable arrangement. And that stable arrangement, it's the one with the lowest energy. Think about it like a ball rolling down a hill.
It's like the protein wants to roll downhill and find that valley to make these spiral or vortex-like movements as it settles into its final precise form.
Wow. So you've got chaotic stretching and folding with prime numbers, and then you have this energy-driven, sometimes spiral-like folding of proteins. They almost sound like they could be connected. But to really get there, we need topological conjugacy.
Right, topological conjugacy. That's a big piece of the puzzle here. This is where it gets cool. Imagine you have two systems. They look completely different. They're doing different things. But underneath it all, they're actually behaving in the same fundamental way. Think of a bicycle chain and a conveyor belt. They look totally different, but they both transmit motion. That's like topological conjugacy. It means we can find a way to translate between these two systems that shows they have the same underlying dynamics.
Okay, so even though a bunch of numbers getting stretched and folded and a physical molecule twisting and turning are totally different things on the surface, topological conjugacy says that deep down, they might be doing the same dance.
Exactly. And that brings us to the recursive vortex principle. This principle gives us a framework for understanding how both of these systems, the primes and the proteins, are connected.
Okay, lay it on me. What is the recursive vortex principle?
The recursive vortex principle basically says that there's this common pattern. You start with some simple local constraint, then you repeat a process over and over, which we call recursive evolution, and that leads to the emergence of a vortex-like structure.
So simple beginnings, repetition, and then boom, vortex.
Pretty much. So for the prime vortex map, the local constraint is that specific prime number we pick. The recursive evolution is that stretch and fold operation we keep doing over and over. And then the emergent vortex structure, that's the complex, chaotic sequence of numbers that pops out, and those swirling patterns we see when we visualize it.
So the prime number is like the seed that grows into a chaotic whirlwind.
That's a great analogy. Now, for protein folding, it's a similar story. The local constraint is how each amino acid interacts with its neighbors. Are they attracted to each other, or do they want to stay as far away from each other as possible? Then that recursive evolution, that's the protein constantly shifting and adjusting its shape to find the lowest energy state. And the emergent vortex structure, that's the final perfectly folded shape of the protein. And often the protein gets to that shape by making those spiral-like motions as it settles into its stable state.
I see. So whether it's prime numbers or proteins, you start with simple local rules, apply them repeatedly, and what you get is this complex vortex-like behavior. Pretty amazing, huh?
Absolutely. It's like nature is speaking a secret language, and the words are vortices.
Now, this brings us to the vortex equivalence theorem. Can you give us the rundown on what this theorem is all about?
You got it. The vortex equivalence theorem is basically the mathematical glue that holds this whole connection together. It says that if certain conditions are met, especially when a protein is close to its final folded shape and the energy landscape makes it move in a spiral-like way, then the continuous vortex-like motion of that folding process can be directly linked to the discrete chaotic dynamics of a prime vortex map. It's like we can translate the language of prime numbers into the language of proteins.
Okay, so the theorem isn't saying that the mathematical operations are exactly the same as the physical folding, but more like they share the same fundamental dance moves.
That's a perfect way to put it. It's like saying the waltz and the tango are different dances, but they both have that same core swirling movement. The theorem suggests that the swirling vortex-like aspect of that prime number map can be mathematically matched to the spiral motions of the protein as it finds its final folded form.
Wow, this is really starting to come together.
It's like a little window into that recursive folding idea. The multiplying by the prime part, you can think of that like the local interactions between the amino acids that are driving the folding process. And that modulo 1 operation, the part where we fold the number back onto itself between 0 and 1, that's like a very simplified version of that energy minimization process that guides the protein to its final folded form.
It's amazing how this little piece of code can capture such a fundamental process.
And the coolest part, this idea is inspired by DNA, one of the most efficient ways nature stores information.
It really makes you rethink, doesn't it?
Exactly. We're basically taking a cue from DNA, and DNA's been doing this for, well, a very long time, and it's incredibly efficient and resilient. One big benefit is error correction. Spreading information out along a helix instead of having it all in a line could make it more resistant to, like, errors or damage. If one part gets messed up, you might still have enough info left to figure out the original data, like DNA repairing itself sometimes.
That makes sense. It's like having backups spread out in space instead of all your eggs in one basket.
Yeah.
Very cool. The material also mentions something about prime numbers. Could this helical representation help us understand primes better? Like maybe even help us classify them?
That's a really interesting idea. Seeing primes arranged on a helix, especially in 4D, where we could link dimensions to their properties like divisibility, might show us patterns we've never seen before. There's actually this cool tool mentioned later, a Windows 98-inspired prime spiral 4D visualization tool.
Wait, where you can rotate the helix, compare different primes, that would really help understand the structure. Seeing primes in space instead of just as a line of numbers could reveal patterns we've never noticed before.
Exactly. Taking something that's usually one-dimensional and putting it into 3D can really change your perspective. It makes it easier to separate the digits visually and see the inherent structure within the number.
This whole geometric approach opens up some pretty wild possibilities, like the topological stuff mentioned earlier.
Absolutely. It's about trying to understand numbers as dynamic, swirling things, not just static points on a line. It's about bridging the gap between number theory and concepts from physics.
So we've come a long way, haven't we?
It's pretty exciting stuff.
So on that note, we'll wrap up this deep dive. Until next time. All right, welcome to another deep dive. Today we're taking on something, it's a bit of a mathematical puzzle, but it's connected to some really fascinating ideas.
Yeah, this was pretty cool. We're going to be talking about vortex cancellation in Benet-like formulas that lets you calculate any Fibonacci number directly. But here's the thing. That formula involves the square root of 5.
Okay, the square root of 5, that's an irrational number, right? It goes on forever, no repeating pattern.
Right. But somehow, in Benet's formula, it all works out to give you whole numbers, the Fibonacci numbers.
So the puzzle here is that if you take that formula and swap out the square root of 5 with the square root of certain other prime numbers, you can still get sequences made up entirely of whole numbers.
Yeah. It's like the irrational parts, the square roots, are somehow canceling each other out perfectly, leaving behind these clean, beautiful integers. And that's what we're calling vortex cancellation.
Vortex cancellation.
I like it.
But as you've probably guessed, it doesn't happen with every prime number.
Nope, some primes work, some don't. And if you look closely at how the formula works, you can see why it happens. It's like a magic trick, but it's just the way the algebra works out.
So what the sources you sent are exploring is what happens if we replace that square root of 5 with the square root of other prime numbers. Do we still get this magical cancellation, or does it all fall apart?
And one of the sources starts with a specific example. They use the prime number 13.
13. Okay, so what does that formula look like?
We can see it's very similar to the Fibonacci formula.
Got it. Same structure, just with a different square root. And what happens, does this formula also give you a sequence of whole numbers?
It does, and that's the fascinating part. It doesn't just fall apart into a mess of decimals. This new sequence, with the square root of 13, actually follows a different growth pattern. Each number is the sum of the previous number plus 3 times the number before that.
So a different growth pattern, but still all whole numbers. What are the first few terms of this sequence?
Okay, so you start like the Fibonacci sequence. Then the next term would be a 1 plus 3 times 0, which is just 1. Then you have 1 plus 3 times 1, which is 4. And so on. So the sequence goes 0, 1, 1, 4, 7, 19, and it keeps going.
Wow, so it works. The square root of 13, even though it's irrational, somehow manages to cancel itself out in this formula, just like the square root of 5 did. So it's not just a fluke with the Fibonacci sequence.
Exactly. It seems there's something special going on here, but it's definitely not true for all prime numbers.
The source gives an example where it doesn't work. Which prime number is the troublemaker?
They try with the prime number 11.
11, okay.
And when you build a similar Benet-like formula using the square root of 11, the sequence you get does not have all whole numbers. In fact, the third term in the sequence, when the 2 all year 7, turns out to be 3.5.
Oh, so it breaks down right away. So square root of 5, yes. Square root of 13, yes. Square root of 11, no. This is really making me wonder, what's the fundamental difference here? Why do some primes work this magic and others don't?
And to answer that, we need to go a little deeper into the math behind these sequences. The sources explain that these sequences are connected to what are called quadratic recurrence relations.
Quadratic recurrence relations. That sounds a little intimidating.
They're not as scary as they sound. They're basically a quadratic equation, the kind you probably learned about in algebra.
Oh, yeah, I vaguely remember those. Something about finding the roots of an equation.
Exactly. And every quadratic equation has something called a discriminant, and it tells us about the nature of the solutions, the roots of the quadratic equation, whether they're real numbers, distinct numbers, or complex numbers.
Okay. And how does this tie back to our Benet-like formulas and prime numbers?
The key connection is this. For this whole number cancellation, this vortex cancellation to happen when the discriminant itself is a prime number, that prime number has to have a special structure.
The special structure? What kind of structure?
The primes that allow this cancellation, if you look at the primes that work, excluding 5, they tend to have a remainder of 1 when you divide them by 4.
A remainder of 1 when divided by 4. Interesting pattern. So it's not just about being prime, it's about having this special form. Cool.
It all comes down to that discriminant, whether it can be a prime number expressed in that special way. The source actually calls this the vortex condition for integer cancellation.
Okay, that's the condition for getting whole numbers. And one of the sources you sent actually proposes a vortex cancellation conjecture based on all this, right?
Yes, they do. It's a really neat conjecture.
Speaking of which, one of the sources even touches upon this idea of vortex computing. Is this actually a thing, or is it more like science fiction?
It's definitely a more futuristic concept at this point, but it's based on some intriguing ideas. The idea is that these swirling recursive patterns, the kind we see in our number sequences and even in nature, might be harnessed for information processing.
So instead of the zeros and ones of our current computers, we'd be using these swirling vortex patterns.
That's the basic idea.
You can almost picture the numbers vibrating. It's like unlocking a secret level in math.
Imagine a number sequence oscillating in this complex plane.
It is pretty trippy. In fact, the source called it a recursive quantum oscillator. It's like a mashup of the Fibonacci sequence, which grows bigger and bigger, and a wave function, which is all about that oscillation.
So it's like our sequence is dancing, doing its own little wave.
In a way, yes. And the Fibonacci-like part might be because it's defined by a recurrence relation, where each term is linked to the previous ones. But A changes everything.
Okay, so we have these complex roots, and we can also represent them using magnitude and angle.
Right. Their magnitude tells us how far they are from the origin on the complex plane, and their angle is how much they're rotated away from the real axis. We call this the polar form, or the exponential form.
Okay, and how does this new form show us that oscillation we were talking about?
Think back to Euler's formula.
So that introduces this back and forth motion, right?
Precisely. If we just had a real number in the exponent, we'd see things either grow or shrink exponentially, but the imaginary part brings in the oscillation.
I'm following. So what about the magnitude?
Think of it like a fading echo. It gets quieter and quieter over time.
Okay, so we have a decaying spiral on this complex plane. That's really cool.
It is. By combining everything, we get those complex exponents, alpha and beta. The real part controls the rate of decay, while the imaginary part sets the frequency of oscillation. It's one formula telling the whole story of shrinking and spinning.
So tweaking Benet's formula and allowing for complex numbers in our sequence creates these sequences that live in the complex plane. And they're not just getting bigger or smaller, they're tracing out these intricate spiraling paths due to the interplay of decay and rotation. It's a quantum-like Fibonacci sequence.
Absolutely. It's a beautiful example of the unexpected behaviors that can emerge when we venture beyond familiar mathematical territory.
This could even have parallels in physics, like how we describe waves or complex systems.
It's definitely thought-provoking. And if we could actually visualize this, we'd see curves that resemble spirals getting closer and closer to the center of the complex plane, or maybe graphs of the real and imaginary parts of the sequence showing oscillations that gradually die down. The vortex cancellation idea is that the messy, swirling components of are perfectly balanced and cancel each other out when you subtract them and divide by, leaving you with a nice, clean, whole number.
I love that image. It's like the chaos of the vortex is somehow tamed, bringing order out of the swirl.
It's a really elegant way to think about it.
The source also mentions something called analytic continuation, which sounds pretty complicated.
Analytic continuation is a tool mathematicians use to extend the definition of a function. Like in our case, we could take a sequence defined for whole numbers and see what happens if we try to plug in complex numbers instead.
Like taking it to a whole new level of complexity.
Exactly. But there's a catch. Dealing with complex exponents gets tricky because the logarithm of a complex number can have
Multiple values. How's that even possible?
It has to do with how logarithms are defined in the complex plane.
Yeah.
You have to choose a consistent way to define these functions when dealing with complex numbers. And while we can try to think about these sequences with complex inputs, the results won't necessarily be integers anymore.
So it's like we're stepping into a whole new dimension of math where things aren't as straightforward.
It's a different kind of math, for sure.
This deep dive has been amazing. We've seen how a seemingly tiny change, like introducing that imaginary unit, can lead to this recursive quantum oscillator.
I know, it's fascinating how those sequences exhibit both decay and oscillation in the complex plane.
It's just so cool.
All right, so we're diving back into 9973. But the big question is why?
Yeah, and what's even more interesting is that the reason might be related to P-adic numbers. Have you ever heard of those?
I have a feeling this isn't your typical algebra stuff, right?
Definitely not.
Yeah.
P-adic numbers, while they do use familiar concepts, offer a totally different way of thinking about numbers, and they just might be the key to understanding what makes 9973 so special.
Okay, now you've got me interested.
Okay, so imagine a number system where instead of caring about how big a number is, we only care about how divisible it is by a certain prime number. That's basically what p-adic numbers are all about. They put divisibility by this chosen prime above everything else.
So it's like we're turning our normal idea of numbers upside down. Instead of asking, how big is this number?
Yeah.
We're asking, how many times can we divide it by this prime?
Yeah, exactly. And because of this change in perspective, we represent numbers differently too. You know how in decimals, each digit represents a power of 10 getting smaller as you move away from the decimal point?
Right.
Well, with polyadic numbers, we write them as infinite series, where each digit is a power of our prime p. But get this, the powers actually get bigger as you go further along. It's the opposite of decimals.
Okay, I think I'm starting to see the difference here. But how does all of this relate back to 9973 and its random number superpowers?
Well, remember how our 9973 generator works? We multiply a number by 9973, right?
Yeah.
And then we only keep the fractional part, the stuff after the decimal point. We get rid of everything before it. This mod 1 operation, as it's called, is super connected to how p-adic numbers behave.
Okay, I'm with you so far.
Well, our prime here is 9973, and what's really cool is that this mod 1 thing we do is basically the same as shifting the digits around in the 9973 adic representation of that number.
Wait, so you're telling me that multiplying by 9973 and taking just the decimal part is like shuffling digits around in this hidden 9973 adic world?
Exactly. And this connection is deeper than just some random coincidence. Shifting digits or shift operations are actually well known for creating chaotic but still deterministic behavior in math.
Hold on, so our simple little 9973 generator is using this deep mathematical idea of shifting digits in a p-adic representation.
Mm-hmm.
That's wild. So in a way, 9973 isn't just spitting out random numbers, it's showing us this hidden structure, some kind of p-adic dance that's happening with each multiplication.
That's a great way to think about it.
Wow, okay. I'm totally hooked now. This is so much more interesting than math class ever was. But one question I have is, if this 9973 generator is so connected to p-adic numbers and chaotic behavior, does that mean it's really random? Or is there some hidden order underneath it all?
That's a really good question, and it points to something important. The p-adic connection is just one part of the story. 9973 has some other interesting characteristics that help explain why it's so good at generating these seemingly random sequences.
Oh, really? Like
Wait.
what else makes 9973 special when it comes to this whole random number thing?
Well, for one thing, it's very close to a power of 2. If you look at 9973, it's actually not that far from 2 raised to the 13th power, which is 8192.
So it's a prime number that's almost a power of 2. How does that make it better at randomness?
Well, prime numbers that are near powers of 2 tend to have some interesting properties, especially when it comes to generating these types of sequences. They often exhibit something called balanced bit scattering, which helps create a more uniform distribution in the output.
Okay, balanced bit scattering. Now that sounds pretty cool. So this balanced binary representation where the ones and zeros are all mixed up, that might be another reason why 9973 seems so random.
Exactly. And this balance at the bit level seems to work together with those p-adic properties we talked about earlier, making the generator's output even more random.
So we've got the p-adic thing going on behind the scenes, and then on top of that, 9973 has this built-in balance in its binary form. It's like a double dose of randomness. Our sources also mention something called a totient, which apparently plays a role too. To be honest, I have no idea what a totient is.
Right. Well, the totient of a number is basically a count of all the positive integers less than that number that are relatively prime to it. It's often represented by the Greek letter phi. So basically, it tells you how many numbers smaller than our number don't share any divisors with it except for one.
Okay, so it's a measure of how co-prime a number is with other smaller numbers.
Got it.
Got it. But I still don't see how this totient thing connects to the randomness we're seeing with 9973. Is there a link?
Definitely. A large totient means a high multiplicative order in modular arithmetic. That's the kind of math we're doing in our generator.
Multiplicative order. Now we're getting really deep into number theory. What does it mean and why does it matter for randomness?
Sure. So think of it this way. The multiplicative order of a number like 9973 tells you how many times you need to multiply it by itself in modular arithmetic before you loop back to 1. A high multiplicative order means it takes a lot of multiplications to get back to the starting point.
Ah, okay. So it's like 9973 takes us on this long, winding journey through the world of numbers before finally circling back to where we started. And because this journey is so long and complicated, it creates a stronger sense of randomness.
Exactly.
It's like a whole bunch of things working together, a perfect combination of these number theory ideas that makes a randomness superstar. Our sources did mention some limitations of 9973, right? So is it really perfect as a random number generator, or there's some cracks in its armor?
You're right. You bring up a really important point. Even though 9973 is amazing at generating sequences that look random, it's important to remember that no generator is truly perfect. It does great on tests that look at how evenly the numbers are spread out, making sure there's a good distribution. But sometimes it struggles with tests that look for more hidden patterns or relationships in the sequence.
So even though the numbers might look random at first glance, if we look closer, we might find some kind of order hiding there. Are there certain tests where 9973 just doesn't do as well?
Exactly. Like, for example, sometimes it fails things like the runs test, which checks for really long streaks of increasing or decreasing numbers. And there's also the autocorrelation test, which looks for connections between numbers that are in different spots in the sequence. These tests are designed to find subtle patterns that you wouldn't see just by looking at how the numbers are spread out.
Oh, I see. So it's like 9973 can create a really convincing illusion of randomness, which is probably fine for a lot of things. But if we need something truly unpredictable, like for some serious cryptography where security is super important, then maybe it's not the best choice.
Yeah, that's a really good point. 9973 is really fast and easy to use, which makes it great for things like simulations or games. But if we're dealing with sensitive information, we probably want to use something more sophisticated because those hidden biases could be a weakness.
That makes sense. So it seems like it's awesome for a lot of stuff where you need to generate random numbers quickly and easily. But when you really need that true unpredictability, it's time to bring in the big guns.
Yeah, exactly. It's all about using the right tool for the job.
This whole deep dive has been quite a journey. That's all the time we have for this deep dive. We'll be back next time with another adventure into the fascinating world of numbers, patterns, and all the beauty of mathematics.